All right, so today we're going to continue talking about Gauss-Jordan elimination, but we're going to look at some special cases that can arise and what they mean and what to do about them. Okay, so let's take a look at example 1. We have a system of equations, and I'm just going to try to apply Gauss-Jordan to it. So I'm going to write the augmented matrix 2, -1, 1, -4, 2, -2. Okay, there's my augmented matrix, and I'm going to apply row operations to it. So I'm seeing that, well, if I take 2 times row 1 and add it to row 2, then that will give me a 0 down in this lower left-hand corner. So I'm going to take row 2 and I'm going to subtract 2 times row 1. Okay, so what does that give me? I'm just going to leave the first row as it is. And then if I take 2 times 2 is 4, add it to 4, I get 0. 2 times -2 gives me -2, add it to 2, I get 0. 2 times 1 gives me 2, add it to -2, I get 0. All right, well, now I'm kind of stuck. Now I could take the first row and divide by 2 to get a 1 in the upper left-hand corner, but still there's no way to get the normal goal matrix, the row reduced form matrix that I like, with 1s on the diagonals and 0s everywhere else. It's not really anything I can do. So let me try to figure out what this is telling me. Now, if I take this augmented matrix and I turn it back into the corresponding equations, this is saying 2x minus y equals 1, right? That first equation. And the second row is telling me that 0x plus 0y equals 0. Now, this is the true statement. This is true for any x and y. So there's no contradiction or anything going on there. So what's happening? Well, if I look back at my original equations, you can see that if I had just taken this second equation and divided by -2, which I can do, it's an equality. If I divide both sides by -2, it should still be true. Then I would get 2x minus y equals 1. So these two lines are really the same line, right? So this would be an underdetermined system of equations. And so what happens with an underdetermined system of equations? It just means that it's one line, and every point on that line satisfies this system of equations. So rather than getting a unique solution, we get an infinite number of solutions. And we call these kinds of systems dependent systems. So they're dependent because, x depends on y or y depends on x. And there is no unique solution. So you get an infinite number of solutions. And all of those solutions lie along this line. So how do we express the solution to this? They're all along this line. And what we do is we parameterize the solution. Okay, so what we're going to do is assign an arbitrary value to one of the variables and then express the other variable in terms of that arbitrary value. And we call that parameterization. We parameterize the solution. So let's see how that's done. So what we can do is we could just say we'll let x equal t. T is a very common parameter to use, and so then we know that 2t is replacing x by t minus y equals 1, and so we can rearrange this to find out that y is equal to 2t minus 1. Okay, so we can parameterize the solution. So we can say that x comma y is equal to t comma 2t minus 1. Okay, so our solution depends on t. We can pick a value for t, and then that will give us the point. Okay, now it doesn't really matter too much which variable you let be t. I could have said let's let y equals t. Okay, this is just an alternative solution, all right? Then then what do we have? We would have 2x minus t is equal to 1. And so if I rearrange that, I can get an expression for x in terms of t. So if I add t to both sides and then divide by 2, I end up with 1/2 t plus 1. Okay. So another parameterization could be that we have the x value is 1/2 t plus 1, and the y value is t. Okay, that would be an alternative parameterization of that solution. All right, so that's how it works. This is the case where we have where we have sort of a sort of an underdefined system. We have two lines that end up being really the same line, and so any point on that line is a solution to the system of equations. All right, well, I'll meet you in the next video to look at the next example.